This is the video for Chapter 4, Part 4. In Section 4.2, we're going to look at the least squared regression line, as well as using that line to make predictions, and then being able to interpret the slope and y-intercept of the prediction line, or the least squared regression line. So there are a few things about the least squared regression line that I want to share. The first is that this least squared regression line will always pass through the point that has the mean of the x's and the mean of the y's. So x bar, comma, y bar. These are the means of the data. The line itself is kind of tells you where the mean should be for the y based on whatever x value you are looking at. The next thing we want to look at is that the least squared regression line minimizes the distances between the point and the line. Now these are the vertical distances, the y, basically the differences in the observed value, the y value, and the predicted value on the line itself, y hat. We call this a residual, and the residual is the observed minus the expected. And we'll take a look at that in a little bit. And then last on this page, I just wanted to mention a few different names that you might hear me use or see the textbook or my StatCrunch or MyLabs Plus use. And that would be the line of best fit, the regression line, or the prediction line. So all of those things mean the same. So one more thing about the least squared regression line, and that's when we're able to use it. So we'll always be able to have StatCrunch give us a least squared regression line, but we won't always be able to use it for predictions. And when we can use it is as long as there is a linear relationship between those two variables. So when the R value is greater than the critical value in the table, and there should be another parenthesis there at the end of table. So let me see if I can fix that. There we go. And then if it's not, so what happens if we don't have that? Well, then we use the mean of the y values instead. So if the R value is less than that critical value, we must use the mean of the y values. So if there's no relationship, there's no effect, basically, the x's are not doing anything to tell us what's going on with the y's, then we would use just the mean of the y values to be our best prediction. So now we want to find out what is the least squared regression line for this data, and can we use it to make predictions? Well, we've actually already answered the can we use it to make predictions, because we have identified that there is in fact a relationship between these two variables. But we do need to use StatCrunch to see what that least squared regression line is. All right, so Part D asks for the least squared regression line, and can we use it to make predictions? Well, our least squared regression line actually shows up in the same results window as the linear correlation. It's that line right there. Time to drill equals 5.52 ... plus 0.011 ... depth of drilling begins. This is a weird way to write the equation as far as what we're used to seeing. We're used to seeing x's and y's. But remember, the dependent variable is the y value, and the independent variable is the x. So when we write this out, we'll do y hat equals, and then our homework asks us to put the slope and x value first, then the y-intercept. So we would write y hat equals 0.012 x plus 5.527. Now that we've identified that we have a prediction line and we can use it, we're going to predict the drilling time if drilling starts at 130 feet. For the next part, we're asked to predict the drilling time if drilling starts at 130 feet. So this is a prediction, so we're not necessarily looking at the data over here where it says 130 feet took 6.93 minutes. That's not what we want. Instead, we want to use this equation that we found to predict what it should be based on this information that we have in order to get this least squared regression line. To do that, we can actually go back into this calculation that we did where we selected the x and y variable. And this is where I said earlier we could use this prediction of y. So if I wanted multiple values to predict, I could do that. I could just put a comma and 150, even though it didn't ask for it, just so you can see what it'll give us. You can always leave this level as 0.95. That doesn't have to change. So just put your x value or values here. And now when we click compute, you'll see a slight difference. Down here, we have to go to the bottom, but we have an x value and then the predicted y value. In this part of our example, we want to identify whether the observed drilling time at 130 feet is above or below average. And to look at that, we just look at our actual value. So for 130 feet, we had a time of 6.93 minutes. And we're going to compare that with the predicted value of 7.03 minutes. And so we see that this number is less, so it's definitely below average. We can also calculate the residual and get this same answer. So our residual, remember, is the observed, which would be 6.93, minus the expected, 7.03. This would give us a negative 0.1. The negative tells us it's below average. Any residual that is a negative number would be below. And the 0.1 tells us it's not really that far away from what we would expect. If we want to put the least squared regression line on our scatter plot or scatter diagram, we can do that with StatCrunch as well. It actually automatically happens when we do our regression calculations, and that's what I'm going to show you on the next slide. Right. So the neat thing about this linear regression option that we have under stat is that along with all of this information, we can also see our graph, our scatter plot, along with a line. So we had that opened up over here. Oops. There we go. So this is what the window we had of just the scatter plot. But this same graph is available when you do the regression calculations. So we have all of our data as well as the graph with the least squared regression line, or that line of best fit. The last two parts of our example are about interpreting or identifying and interpreting the parts of our least squared regression line, starting with the slope. All right, so I've written out our regression equation, our least squared regression line here at the top, and our slope will always be the value with the variable. So we'll be looking for whatever value has that x with it. And in this case, we've got 0.012. And in order to interpret this number, we need to know its units. And so I wrote out what our units were for x and y. Remember, x is the starting depth, so that's in feet, and y is the time it takes to go 5 feet, to drill a depth of 5 feet, so that's going to be in minutes. Now, if you think about slope, back when you were doing slope in an algebra class, you might remember that the slope is rise over run. And that ends up being the difference in the y's over the difference in the x's. So our units are going to be the units for the y's over the units for the x's. So in this case, it's going to be minutes per foot. And so to interpret that with words, with a sentence, we would say that for each additional foot in starting depth, because that's what our X value is. So for each increase that we do, each additional foot that we go as our starting depth, we can expect about 0.012 of a minute additional time to drill 5 feet. Now, this doesn't have anything to do with the actual question, but writing out 0.012 of a minute is not very helpful for me to know how long that is. And so if you're ever curious, or if the question actually does ask it, then we can change minutes to seconds by taking that part of a minute times the number of seconds in a minute is going to give us 0.72. So not even a whole second. So not only is it a small portion of a minute, but it's not even a full second that we're going to add to the time. But that's a side note. So we'll kind of... That's just because I'm usually curious about what those numbers actually mean. And then finally, we want to be able to identify the y-intercept. That part's easy because just like identifying the slope's going to be the one with the variable. The y-intercept is going to be the one without the variable. It's going to be the constant term. The hard part is to know whether or not it's reasonable to interpret the y-intercept. And for this problem, if it is reasonable, we want to interpret it. So what does it actually mean to be reasonable to predict or to interpret the y-intercept? So we've got two questions we can ask ourselves to say whether or not it is reasonable. And these two questions are in your interactive assignment. The first one is 0 a reasonable value for x? And in this case, I think it would be, because if you started at a depth of 0 feet, you would just be starting your drilling on the surface. And so that is reasonable. And do any observations near x equals 0 exist in the data set? Now, in that case, the question comes down to, is 35 feet close to 0? And that can actually kind of go either way, because we go all the way to 190, and as far as that's concerned, 0 is really not that far away. So I'm going to go ahead and interpret it, and then just make sure you're careful with interpretation of the y-intercept. So in this case, the y-intercept is always the point 0, comma, and then whatever the y-intercept is in your equation. So in this case, it was 5.527. So what that means is that at a starting depth of 0 feet, we would expect it to take 5.527 minutes to drill 5 feet. So, in this case, this second question is actually kind of iffy as far as whether or not 35 feet is considered close to 0 feet. If we're talking about heights, then no. But if we're talking about depth that go all the way to 190, then maybe. So, you know, I just kind of have to play it by ear. Most of your examples either just ask you to give you an equation and ask you to interpret the y-intercept, or they give you something that is obvious as far as these two things go.